SwayamPrabha. Digital India. Educated India.
So, welcome to this continuation of this lecture. So, we are talking about the two-dimensional equations. So, where we have two equations, so we have to manage or handle these two equations together simultaneously. So, that is the important part. So, tomorrow if you take up another fluid mechanics problem, you may have to deal with three equations. So, this is a very important exercise, how to deal with more than one equation at the same time. So, we quite often the equations are quite similar, but however we have to handle them together. So, this is first equation which we have put here as a weighted residual and including the boundary term. Okay, so this boundary term is integrated over the traction boundary. So, similarly, the second equation looks like the same thing, very similar to this one, and again we have a weighting function and the equation is dou dxy by dou x plus dou sigma y by dou y plus y bar is equal to t sigma, and the weighting, so the traction boundary condition here is tau x y and x sigma y and y minus dy d gamma is 0, right? So, this is okay. So, we are dealing with both these equations together, and so the weak form of this one, let us do the weak forms also. The weak form of the first equation, in fact, let us see here there are two weighting functions here, so they can be different. So, this can be wi comma 1, this is wi comma 2, right? This is a comma 1 and I comma 2. Because two equations, so the weighting functions may be related or may be different. Okay, so the weak formulation is, we will do this one. So, sigma x is still there and it looks like it is first derivative on sigma x, but it's more than that because sigma x is related to epsilon x straight away with this t, and then the strains are related to stress displacements by another derivative. So, this is actually a second derivative of displacements. So, what we do here is do the integration by parts using the Green's lemma, just like we did it in heat conduction. So, it looks like this: wi comma 1 sigma x nx, and let me, this is the first term, and the second term or tau xy and y. So, this is the integral on gamma, okay, full gamma, and plus it is the derivative on wi sigma x wi derivative on wi1, the y derivative, tau xy, and integral over omega, and one more term here because of x, looks many terms. And the last term here is on gamma q is as it is. Okay, looks like many terms, but many of these terms may get cancelled. So this, go to the second equation just now, but for this simplification, so this gamma is actually gamma on displacement and on traction boundary. So this has the complete gamma can be put as a boundary on U and a boundary term on traction. Yeah, traction. This is, I think I'll calling it as gamma T. So there is some amount of confusion here. So let me put it as the traction boundary condition. Either I'm using it as T or Q. Q is in relation to the heat condition. T is more akin to the solid mechanics application. Okay, so now as usual, we can cancel some of these terms by the choice of W prime I1 as Wi1, a negative value. What is this it's going to do? So here the terms, here this and the whole thing here, of course Wi comma 1 can be taken out, and right, so it can be cancelled of gamma T. So that only leaves gamma U, and we can also do that now that we are used to it, and also Wi comma 1 is 0 on boundary gamma U. So by doing that, so in one case this is getting cancelled with this one, in the other case Wi comma 1 being 0, so that gets cancelled on gamma U, right? And oh, I'm sorry, there's yeah, so that gets this one completely gone apart with this one. And finally what you have here is, yeah, there's a small mistake here. I think when you do the integration, so this becomes negative actually. Okay, yes, so if that's the case, then what we have here is simply, I'll just put it here. So I'm just correcting the tabs. This becomes Wi comma 1 and together with the Tx. Okay, so we cancelled many terms. So then what we have here is the integral of this one, okay, with the negative sign, and then we also have the integration because of this x bar, which is the body force, and with the traction boundary condition here. So this becomes negative, okay, and because that's what is assumed here. So this is the simplified version of this long equation. So similarly, we can also do it for second equation. So second equation, so similarly, weak form of the weighted residual equation 2. So what we get is very similar to that. I'll directly write it. So we use I comma 2 here, dou x, tau xy here, okay, that's tau xy, and dou y of sigma y, okay, here, plus wy comma 2, the body force y here, and wy comma 2 on gamma t of t bar y. Okay, exactly, very similar to this one, but it is the equation like this one. So looking at this one, so let's do it in the matrix form, which makes it concise. Okay, so what we do here in the matrix form, so what we write, so both the equations we'll write it as 2 rows of the matrix. So they say so just see this one. So this is the first row. First row means first belong to first equation. So I am taking the terms related to W out, multiplying sigma x, sigma y, right? So, so it is giving the first row gives dou wi comma 1 dou x times sigma x and dou wi comma 1 dou y times tau xy. So that's what this equation is, right? So similarly, the second equation refers to this one. So this is this first part, and the second one wi comma 1 0 wi comma 2 x bar y bar d omega, right? So this is this one, and the last term exactly resembles this term, gamma t tx and ty is equal to 0 here. So 0 also has 2 components. Okay, so this is how we put it in the matrix form, right? And so this is a little easy to handle, right? Instead of these long equations. And moreover, here what it is that all the approximations are 2 variables now, and then which we can put as a vector. Okay, so now once we have this one, interestingly this is the one which is, this first one is the one which is going to lead to the K matrix, and the other two can be taken to the right side, and they will become F vectors. Okay, so let me just put that. So in that process, let me also simplify it to some extent. And what is sigma x, sigma y, tau xy? So sigma x, this also has to be written in terms of displacements. So how do we do this one? So this is the D matrix here, D1, 1, 1, 2. Okay, so this we'll write it as D times epsilon x, epsilon y, and so on. So this is nothing but dou u by dou x, dou v by dou y, dou u by dou y, plus dou v by. So everything we'll try to put it in terms of u and v. So we want to take uv out of this one. So that can be done by taking this as operator, d dx dou y, this is the operator acting on. So now you can see that this epsilon x, epsilon y, epsilon gamma xy is nothing but dou x on u, right? And this second one is dou y on v, and the third one, gamma xy, is dou y on u plus dou x on v, right? So this is how we can simply write it as d times, we'll write it as L. Okay, so all these things, earlier this variable used to be only 1, now it is 2, having components 2, so it's a vector. So d times L, L is here an operator, is nothing but dou x. Okay, so it looks very concise now. So that is sigma x, sigma y, tau xy. And what about this one? So let's also do this. So it is dou wi1 So what we do here is that we will write the as the transpose, just a minute. So this is nothing but the transpose of this one. Because when we write it as a transpose, we will be able to express it similar to this, the last expression. So whatever we have here, it is nothing but the transpose of this one. So this we can write it as So many things get repeated. So the whole thing here, this 3 by 2 thing, can be written as this operator operating on this 2 by 2 matrix. So you can see here very well that this is nothing but the first term, for example, is nothing but dou x0 operating on this one. The second term here, dou x0 operating on this one, which turns out to be 0. So like this. So this is exactly same as this. So what are we trying to get? So if you can try to see the similarity between this step and the earlier step, so this is nothing but your L. Okay. So like this, so we have this also same as that. So now let's rewrite the whole thing. So I'm just trying to put it here. Dou x of, what is this one here? This is nothing but your here L times u v L times dl times u v. Okay, so this is how we have put the first one with a negative sign here, and again I'm repeating. In fact, we can even this plus this with a negative sign of that being 0. So we'll just remove this negative sign and then we'll take it to the right side. Okay, so looks a little bit better, and then now let's do the simplification for one element. So what is that which we are dealing with? The approximations will come on the displacements here, right? Displacements have to be appropriately approximated, and of course the weighting functions obviously will be the same as the trial functions. Okay, so they will not be very much different. So we have to express this. So this u hat and will be functions of xy. And these things, what we have to assume here, what are the minimum conditions on this u hat and v hat, depends upon the operator here. What is these derivatives that are operating on u? If you look at this operator L is nothing but the first derivative. So that means that the approximations u hat and v hat has to have first derivatives within the element. Okay, a well-defined first derivatives. And on the other hand, if they have any discontinuity, so which will be at the element boundaries, has to be finite discontinuities. The derivative has a finite discontinuity which means that the function is a continuous function. So C0 continuous. Okay, so this is in 2 dimensions. So in 2 dimensions here, in 2 dimensions. So the one which we take is the triangular element. This also we have done in the case of heat conduction problem. So a triangular element with 3 nodes like this one will be, for example, U, which we write as A plus Bx plus Cy, which is equivalently written as Ni phi I plus Nj phi j. So this is straight away in terms of polynomial terms, whereas this is in terms of the nodal values here. So it is not phi here, it is U, Ui, Uj, Uk. This is Ni, Ui, Nj, Uj, Uk. So similarly we have here for, we can also do it for V is same thing as, so it's Ni, Vi, Nj, Vj, Nk, Vk. Okay, so what we have here then is the shape functions Ni. The same shape functions are being used for the U's and V's, and now so what we write here is, we wrote it as 2 components, but then we would like to write both of them together. So that means that U and V, we'll write it as Ni 0, 0 Ni, Ui, Vi, Okay, so it looks the things have become bigger, but it's not really that complex. It's only that earlier we used to have a simple 1 variable expression, something like phi is Ni phi I, Nj phi j. Now what happened is that this is also like that. Now we have 2 variables uv, it's n, that variable phi, if you call this phi, having 2 components, n is having 2 by 2, so phi I, phi j, phi k, right? So that means that those phi I, phi j, phi k have now become 2 components. Okay, so this is uv, and so these are the shape functions, right, which we use for the approximation of, we know what Ni is. Ni we know for a triangle. For a triangle, so we know Ni is nothing but Ai, Ciy, and so similarly. So this is what we are going to use a little later. Okay. So now what is that which we need to do? So what we need to do here is that what will be the weighting functions. Now once we know the weighting functions and once we know this uv here, so what is this first integral? Let's look at the first integral. Integral is that, what is that which we have here? L operating on the weighting functions. So now we know that the weighting functions are same as trial functions or shape functions. So that means that this wi comma 1 and wi comma 2, what will be this? So this will be same as the shape functions, this or this or this. I'm sorry, this is J. So either this is shape functions or Nj or, so that means that we will use these shape functions to derive two equations at node I, two equations at node J, and two equations at node K. So what it will be totally? There will be 6 equations. Corresponding to node I, we have 2 equations, right? And corresponding to node J, we have 2 equations. And corresponding to node K, we have 2 equations. So that means that in this equation now, for the weighting functions, so we use in this place Ni and Ni. So then this uv here, so uv as shown here will be this whole thing, right? And so that means that this will have kind of 3 components. So this will have just that 2 by 2 component, and then this L has to operate on Ni. Okay, so let us see that how L operates on Ni in our next lecture. So for the moment, we will just pause it. Okay, we'll just pause it here, and we'll continue in our next lecture from this set of equations. So once you should try it at home. So what will be? You put it here, L we know what? L. So L operating on Ni. So please do that before coming to the next lecture, so that will be a little instructive, and then that will give you a feel for handling a set of equations. It is just not one equation. It has a set of equations, so that will be a good exercise. So for the moment, we'll stop here.